Okay, so this is a review of trigonometry without a hand trick. Some people probably learned ways to find trig functions of an angle using their hand. I never understood it, so I just going to try to teach you the way that I remember how to do trigonometry. And if it works for you, great. If it doesn't work for you, if you have another method or remember another different way, that's fine too. So you don't have to do it my way. And a lot of times in this class, there are different ways to do things. And I will show you the way that I prefer. You don't have to do it that way. Okay? You just got to make sure whatever you're doing it correctly. Okay? What I like to remember is 4 things to understand trigonometry. First one is just your simple SOHCAHTOA mnemonic that helps you understand the relationship between a trig function of an angle and the sides of a right triangle. So the sine of an angle is equal to the ratio of the opposite side with respect to that angle over the hypotenuse of that right triangle that angle is in. You have cosine, and this is theta, which can be just a variable like x. It's just the typical Greek letter that we use for angle measurements. Cosine is adjacent over hypotenuse. Tangent, opposite over adjacent. Okay, that might be fine. Do we remember our reciprocals? So the reciprocal of sine is what? It would be hypotenuse over opposite. What would be the trig function that we use? Cosecant, yes. CSC, cosecant is the reciprocal. And the reciprocal of cosine is secant. And the reciprocal of tangent, cotangent. Okay, that's the first thing we need to know. Second thing is we need to know measurements of a 30, 60, 90 and a 45, 45, 90 triangle with a hypotenuse of 1. So if this is the right angle and that's the hypotenuse, they both have the same measurement of 1. Well, the way that this 30, 60, 90 triangle right here is oriented, we have the larger angle here on the bottom, the smaller angle towards the top. The smaller side of a 30, 60, 90 opposite the smaller angle is 1/2. The larger side opposite of the 60-degree angle is √3/2. That's how I think of the comparison of 1/2 and √3/2 as a smaller and a larger side. 1/2 is less than √3, which is 1.7 something over 2. 1.7 over 2 as a decimal, or √3/2, is 0.866. So 0.866 is definitely bigger than 0.5. So I like to keep that distinguished in my brain. Of course, you can orient this triangle where the smaller angle is on the bottom here. It's good to know the 2 different orientations you will see in your unit circle, either the larger angle 60 degrees on the bottom or the smaller angle on the bottom, which means our shorter side is this vertical side and our longer side is this horizontal side. Then your 45, 45, 90 triangle, isosceles triangle, simple. Both sides are √2/2. Okay, you understand SOHCAHTOA, you understand those triangles. Third thing you need to understand are radian measurements. Where do they come from? And how can we locate them easily? Now I'm going to produce the unit circle up here with all of the different measurements. But your goal, and some of you might not have accomplished this goal last year, is to be able to find out the location of a radian measurement without producing the circle every single time. You need to be able to think, oh, 7 pi over 6, that's going to be here. Okay, you have to do that. In this class, you will not have the time to write out an entire unit circle when asked a problem. You need to be able to do things a little quicker. And I'll show you how I get there, maybe to help. Okay, the important thing to know about a radian is that it's just a distance. It's a distance around a unit circle, or a circle with a radius of 1. Okay, so distance around the unit circle with a radius 1. So that means this length from the origin to the edge of the circle, that's 1. All these lengths of these lines are 1. Well, what we do is we start at this point on the circle, and we say this is our starting point. That's a distance of 0. If you start at the circle there, you have traveled no distance to get there. But we go all the way around the circle, and how we travel on the circle is, this is a positive distance if we go counterclockwise. If we are going clockwise, that's considered a negative distance. Okay? Now, what would be the total distance traveled if we go around this circle with radius 1 and back to where we start? What's that total distance there? 2 pi is correct. And where does the 2 pi come from? Well, it's simple. If we remember geometry, the circumference of a circle has a formula of 2 pi times the radius. Well, if your radius is 1, your circumference is just 2 pi. So if I go around this entire circle, I've traveled a total distance of 2 pi units. If this was exactly 1 foot from here to here, I will have traveled a total distance of like 6.28 feet. Okay? Well, what you think of as 2 pi, you can also think of in terms of degrees as 360 degrees around an entire circle. Now, a great thing about 2 pi is that that's the number, that's the truth, that is the distance traveled. 360 degrees is an arbitrary number that somebody came up with back in the day. If you think about it, where does a degree come from? Well, I think that around a circle they said, let's make it 360 because you can divide it evenly by a lot of numbers. You can divide it by 60, you can divide it by 30, you can divide it by 90, you can divide it by 2, you can divide it by 4. So that's why 360 works. Okay, well, what we're going to do is go around the circle to get all of these different measurements. So like from here to here, how much is that? And we'll notice that we create an angle that is going to be familiar. So I'm going to take this entire circle, split it up into 12 different pieces. If I divide both of these by 12, I'll get that a pi over 6 radian distance is the same as a 30-degree angle. So that means from here to here, if this was pi over 6, this angle right here would be 30 degrees. Now, what do? I can add another pi over 6 until I get all the way over to 2 pi. So if I add a pi over 6 to pi over 6, I have 2 pi over 6. I keep going, I have 3 pi over 6, 4 pi over 6, 5 pi over 6, until I get halfway around the circle, or 6 pi over 6. Well, halfway around the circle, that's like 180 degrees out of the 360. That's equivalent to pi. As you notice, I did not simplify these, but I can. 6 pi over 6 is equivalent to just pi. The 6's cancel. 2 pi over 6, I can divide the top and bottom by 2. We get pi over 3. Divide 3 pi over 6. That is pi over 2. 4 pi over 6, 2 pi over 3. 5 pi over 6 cannot be reduced. 6 pi over 6 is pi. And we can keep going all the way around. This would be 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. And 11 pi over 6. Okay, so those are all the important angle measurements of the unit circle now. Now you can see that this is a 30 degree. Well, if I add a pi over 6, that's an adding another 30 degrees. That would make this a 60 degree measurement from the x-axis up here. And if I came over to the other side, this pi over 3 is also a 60 degree measurement from the x-axis up there. And this guy's a 30 degree. Okay, some things that I noticed that help me remember locations of angles. You see a 3 in the denominator after simplifying your radian measurements. 2 pi over 3, 4 pi over 3, 5 pi over 3. You notice those all create 60 degree angles with the x-axis. So some number pi over 3 gives me a 60 degree measurement with the x-axis. Well, what I can do with all of these 60 degree angles is make triangles. And I notice that what is created are these tall 30, 60, 90 triangles, where the larger side is the vertical side, and the shorter side is the horizontal. So pi over 3 gives us 60 degrees, which gives us what I consider my tall 30, 60, 90 triangle. This is just a number symbol, pi. So some number pi over 3. That is after completely reducing things. You don't want to say, 3 pi over 3 is a 60 degree angle. What else do I notice? I notice that if you have a 6 in the denominator, all of these angles create 30 degree measurements. With respect to the x-axis. Or if I start connecting, they make my smaller, I would say shorter, 30, 60, 90 triangles. And then we should know that in between the pi over 4s, anything with a 4 will create a 45, 45, 90 triangle. And you can think about walking around to get to this. This would be just 1 pi over 4, equivalent to 45 degrees. If you divide this by 8, 2 pi over 8 would give you pi over 4. 360 divided by 8 will give you 45. This top would be 2 pi over 4, which is pi over 2. This would be 3 pi over 4. 4 pi over 4, 5 pi over 4. 6 pi over 4, 7 pi over 4. Now, one thing I want to add in is locating angle measurements without creating the unit circle. just was starting with a x and a y axis. So if I asked you to draw the location of the angle 7 pi over 6, could you do it? Well, maybe some of you can, maybe some of you struggle with it. The goal is to be able to do this without creating the entire circle. I'll show you what I do. If I just have an x and a y axis and I say, where is 7 pi over 6? I say, okay, well, let me think. I know an easy one that I remember. 6 pi over 6 is just pi. Pi is halfway around the circle. I know pi is 6 pi over 6. All I have to do is add a pi over 6. Now let's think, if I'm going around the circle this way, that's adding, going in a positive direction. If I'm going around the circle this way, that's a negative direction. So if I add a pi over 6 here, that'll be going that way. And all of a sudden, this must be the location of 7 pi over 6. What about 5 pi over 3? If I don't have the unit circle, can I locate where 5 pi over 3 is? Hopefully, yes. What I do is I say 5 pi over 3 is close to 6 pi over 3. 6 pi over 3 is 2 pi. Well, where's 5 pi over 3? It is 1 pi over 3 away from 6 pi over 3. It is just subtracted from 6 pi over 3. So if I take and I go this direction and I subtract a pi over 3, and since I know a pi over 3 is going to be a 60-degree angle created, I'm going to be more down here. This would be a shorter triangle. This would be one of my longer triangles. So if you know your pi and your 6 pi over 3, if you know pi over 2, 3 pi over 2, and you convert it into something over a 3 or something over a 6, you can use that to your advantage. Just like 2 pi over 3. 6 pi over 6, the same as 3 pi over 3, which is the same as pi. If I want to go to 2 pi over 3, what can I do? Subtract a pi over 3 from 3 pi over 3, and boom, here's 2 pi over 3. Okay? Goal is for you to be able to do that yourselves. Okay, good. Now, let's put it all together. So we have this unit circle with these distances and radians creating these 30, 60, 90 triangles and these 45, 45, 90 triangles. Another thing that helps, this is not huge, is this mnemonic, all students take calculus. This shows you which trig function is positive in which quadrant. Have you guys all heard of this one? Okay. Anybody use anything different besides all students take calculus? No? That must have been it. So just sine is positive in the second quadrant, just cosine in the fourth, just tangent in the third. Great thing about unit circle trigonometry is whenever you're dealing with, say, sine or cosine and you have a hypotenuse to worry about, sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, the hypotenuse is always 1. So the sine of the angle is just equal to the opposite side length. The cosine of an angle on the unit circle is always equal to the adjacent side length. Opposite over hypotenuse, and the hypotenuse is 1 is just opposite. Well, why does that help me? Well, when we create all of these triangles, maybe if I do over here, when we create these triangles when we're talking about these angle measurements, I create this triangle right here, we're going to be looking at this angle right here as kind of our reference angle for our sides. So all of a sudden, this is the opposite side, and this is the adjacent side here. For 2 pi over 3, this triangle is created. Here is my reference angle. This is my opposite side, and this is my adjacent side. No matter where my triangle is, we'll notice that the opposite side is always going to be this vertical distance. The adjacent side will always be this horizontal distance. So instead of worrying about opposites and adjacents with unit circles, you still have to worry about it, but you can change it kind of to vertical and horizontal and vertical distance, horizontal distance. And you could go even a step further, because what you will notice is that, yes, we create these triangles, but that's just kind of a way to get myself from point A to point B with an x distance and a y distance. All of a sudden, you will notice that we have coordinates on my unit circle that are composed of an x distance and a y distance. That come from my 30, 60, 90 triangle. So if you wanted to, you could do, this is the y coordinate of wherever my radian measurement falls on my unit circle, and this is the x coordinate. You could do it that way. Some people do that. What I do is I stop right here, and I just think about my triangles and my vertical distances and my horizontal distances. Because I can picture the triangle in my head, and I can think about shorter sides and longer sides and which one works. Okay, so I'm going to put it all together. I'm going to find the sine of 2 pi over 3, and I'm not going to look at the unit circle I just created. I'm doing this just from my brain. I will sometimes draw down on my paper a quick little coordinate plane, thinking about a unit circle around that coordinate plane, just so I have my extremes that I know of, and I can kind of reference off those extremes. I'm thinking 2 pi over 3. All right, well, 3 pi over 3 is here. Subtract the pi over 3, and we have 2 pi over 3 up here. That's the first thing I do, only I'm doing this in my brain. Then I'm thinking, okay, sine. Sine just deals with the opposite, or the vertical, or the y. So on this triangle that is created, this is a 30, 60, 90 triangle. Now, is it the tall triangle or the short triangle? How do I know? Well, it's a pi over 3. Since it's a pi over 3, we know we create this tall triangle with the 60-degree angle. Boom, there's my tall, there's my short. This has to be the 1/2. This is the root 3 over 2. That is what I'm picturing in my head. 2 pi over 3. Okay, sine is the opposite side. This opposite side is longer than this adjacent side. The vertical side is root 3 over 2, and that is my answer. Also, since sine is positive in the second quadrant, I make sure that root 3 over 2 is positive. And actually, this 1/2, this would be a negative 1/2. I'm going left on the x-axis. If I'm going left or down, that's like in a negative direction on the x and y-axis. All right, let me do another one. Cosine of 7 pi over 6. Try to do it as well. If you think you can, go for it. If you can't, listen to me go through my process again. I first find out where the angle is. Use the extremes to help you. 7 pi over 6 is close to 6 pi over 6. 6 pi over 6 is the same as pi. Seven pi over 6 is plus 1 pi over 6. So I add a pi over 6, and boom, I'm at 7 pi over 6. Now, pi over 6, that creates my 30-degree angle, so it's my short 30, 60, 90 triangle. Which means my short 30, 60, 90 triangles, the adjacent side is the horizontal distance, is the longer side. The vertical side, my vertical distance, my opposite side, that's going to be the shorter. So this is your root 3 over 2, and this is 1/2. Now I'm going left and down, so these should both be negative. Cosine deals with that horizontal distance, that adjacent side. That is why this is negative root 3 over 2. One more. I'm going to do the secant of 5 pi over 3. What am I thinking? Where is 5 pi over 3? Well, I know where 6 pi over 3 is. 6 pi over 3 is the same as 2 pi. I will subtract a pi over 3. So I'll be going clockwise to get to 5 pi over 3. But knowing that I have a 3 in the denominator, I will have my tall rectangle, triangle created, 30, 60, 90 triangle. So this all of a sudden is 5 pi over 3. So we're in the fourth quadrant. Okay, secants. Well, let's first get the sides down. I know this is my shorter side, this is my longer side. Since it's my tall 30, 60, 90. Secant is the reciprocal of cosine. Okay, so I just need to figure out what 1 over cosine of 5 pi over 3 is. Cosine of 5 pi over 3, cosine is that adjacent, it's that horizontal. It is 1/2 in this case, this horizontal distance. So I have 1 over 1/2, which is 2. When you divide fractions, the same as taking the numerator and multiplying it by the reciprocal of the denominator. All right, before we go on and you guys do some, I want you to do me a favor right now and say hi to your neighbors. Introduce yourself if you don't know each other, because most likely we'll be sitting in these seats for the rest of our time here in this class. I'm talking the entire year. I've not changed the seating chart once. So you need to be comfortable with the people you're sitting next to. You need to be able to use everybody you're sitting next to. We don't do group work in this class, but we do group check. So this is an example of group checking. You guys will do these 3 problems individually, and then you're going to check with a neighbor to make sure you understand. If they can help you, boom, you get that immediate feedback. If you're both confused, or if you just need help before you even start, you can ask me, okay? So before we do these problems, say hi to everybody around you. Don't be shy. You're seniors now. You're a little more mature. This isn't that awkward. Okay, go. Okay, now Do these 3 problems and check with your newly acquired neighbor friend. Or friends, all friends. Check with every single person. You need to do the cosecant of 5 pi over 6, sine of 5 pi over 4, and the tangent of 11 pi over 6. Now, we didn't do tangent, but just remember it's going to be your opposite over your adjacent, which is your vertical over your horizontal. And you are attempting to do this without looking at your unit circle that you created. Yeah, this is 5 pi over 4. Thank you. I had your sister, didn't I, Miss Gilman? Cool. She say good things about me? All right, good. Mr. Owen.
Measurements are the 245s up here.
So the 45s are all the pi over 4s?
Pi over 4, 3 pi over 4.
Yep, because this is 4 pi over 4, right?
Right.
Pi is also 4 pi over 4. Subtract a pi over 4, 3 pi over 4.
Okay.
So if I'm going to add a pi over 4 to 4 pi over 4, what's this one? 5. And then this one would be what? There you go. Mr. Wolf, right?
Yes, sir.
How's it going?
Good, how are you?
Good. Payne Yonzik? Yonzik. Cool. Come see me after class real quick. Okay? You're not in trouble. Don't worry. Wezio? Wezio.
Okay.
No, I got it. Welsh. Okay.
Right, and the multiply.
Keep the numerator the same. Flip the denominator.
I did it.
Multiply.
Yes, yeah, flip the numerator. Yes, the numerator stays the same as the denominator. Yes.
How do I say your name?
My first one.
Both.
Both lines. I go by Michael.
Michael. Okay.
And my last name is Sway.
Sway. Cool. Cool. Thank you. Mr. Meyerhofer, did I have your brother? Did he say good things? It's not there? Yeah. Mark. Yeah. Okay. Did we check? Cosecant, I'm thinking sine of 5 pi over 6. 5 pi over 6 is 1 away from 6 pi over 6. So we're in the second quadrant. We create a short 30, 60, 90 triangle. Sine being the vertical side, the shorter side, that's 1/2. Take the reciprocal of 1/2, or if I do 1 over 1/2, I get the same answer as the secant of 5 pi over 3, which is 2. I'm thinking, is sine positive in the second quadrant? Yes. I'm going up, or I'm in the second quadrant in the S where sine is positive. So cosecant is also positive. Sine of 5 pi over 4. I'm thinking, where's 5 pi over 4? 4 pi over 4 is where pi is. Add a pi over 4. All of a sudden, I'm down here in the third quadrant. We know it's going to be a root 2 over 2 because that's just the pi over 4s. It's either, it's the same for sine and cosine. But sine is negative in the second quadrant since I'm going down. So this is negative root 2 over 2. Tangent 11 pi over 6. Where's 11 pi over 6? Well, I know where 12 pi over 6 is easily. Subtract 1, I get to 11 pi over 6. So 12 pi over 6 here, 11 pi over 6 here. Opposite over adjacent, vertical over horizontal. Well, the vertical side is going to be the shorter side because we have this 30-degree angle creating the shorter triangle. So that will be a 1/2, but it's a negative 1/2 because I'm going down. I'm going to the right. That's the root 3 over 2. And then we just have to remember how to deal with fractions. Keep the top the same, flip the bottom. And last year you were required to simplify this always. This year you won't have to unless you're forced to find your answer on some multiple choice and you don't see negative 1 over root 3. So this is a completely fine answer. This is the correct answer. There's nothing wrong with having a square root on the bottom. But we teach rationalizing so that we have these standardized looking answers, which is why you were taught to change this into negative root 3 over 3. Okay? This is sufficient for a free response question. This is probably what you might have to come up with if it's a multiple choice question. And of course, you know on AP tests, there's multiple choice and free response. You will hate both equally. Guaranteed. All right, next, dealing with extremes. Just remember, cosine of an angle is your horizontal distance. Sine is your vertical. Horizontal can be considered the x-coordinate. Sine can be considered the y-coordinate. Whatever you want to think of. I think distances horizontal and vertical rather than coordinates x and y. So if I ask you what the cosine of 0 is, well, first I got to figure out where 0 is. And I kind of do make a triangle, but instead think about the distance that it takes to get from the origin to this point on your unit circle. Here's your circle. Yep. Okay. Of course, the distance to any of these is 1, right? So this is 1, to this is 1, to this is 1. But it's the horizontal or the vertical distance. Well, I'm going to the right 1. I'm not going up or down at all. Which is why this x-coordinate is 1. Say horizontal distance of 1, this y-coordinate is 0. Which is why the cosine of 0, the horizontal distance traveled, the x-coordinate is 1. I asked you what the sine of 0 was. You can think, I don't travel up or down from the origin all the way over to that right spot on the unit circle where 0 is. So the sine of 0 is 0. This is the up and down. If I looked at pi over 2, well, from the origin up here to pi over 2, I'm thinking about my vertical distance or my horizontal distance. Well, I'm going up 1 to get there. I do not go left or right at all to go from the origin there, which is why this x-coordinate is 0, this y-coordinate is 1. Sine of pi over 2, that vertical distance is 1. The y-coordinate is 1. Cosine of pi over 2 is 0. I'm not going to the left or to the right at all. Okay, you guys do the next two, and then I'm going to give you two more. So do the sine of pi, the cosine of 3 pi over 2. Then do the secant of pi over 2. And the cosecant of pi. No, cosecant of 3 pi over 2. All right, do these four, and then again, check your answers with your neighbors, please. I'm not sure if I told you guys about the BC test that you could take if you take this class. If you're in this class and you're doing extremely well, I encourage my students who are doing extremely well to push themselves a little bit harder and to take the BC test, even though they're in AB calculus. You can do it. It's possible. You just sign up for the BC test. I had 6 students do it last year. 4 of them got 5s. The other 2 didn't study for the BC material at all. However, one of them got a 3 because he got a 5 on the AB stuff. And, you know, he didn't do that poorly, I guess, on the BC stuff or studied well. The other one got a 2. She didn't study at all, but she got a 4 on the AB score. And the BC test gives you an AB subscore. So you kind of take both the AB and the BC test all at the same time. So if you can't take BC calculus, but you want to take the BC test, you can do that in my class. Okay, check your answers, please. Mr. McBride, no problem. Did you check with Annie? How do I say your last name? Lua? Say it again. Lua. Lua? Lua. Neither. Say it again.
Lua.
Lua. I'm going to try. Okay, and it's Annie? Okay, thanks, Annie. Did you get it? Okay, check with Annie. Okay, sine of pi, pi's over here. I'm not going up or down at all. 0. Cosine of 3 pi over 2. 3 pi over 2 down here, not going left or right at all. 0. Secant of pi over 2. It's really the reciprocal of the cosine of pi over 2. 1 over the cosine of pi over 2. Cosine of pi over 2 is 0. This is 1 over 0. That's not 0. That is undefined. We will discuss what it looks like around 1 over 0 to the right and to the left of 0 in the future. And the cosecant of 3 pi over 2, well, that's really the same as 1 over the sine of 3 pi over 2. Sine of 3 pi over 2 is -1. 1 over -1 is -1. Since I'm going down here to get to 3 pi over 2, that is down 1, or down a distance of -1. Okay, good. Next, quickly, we're going to discuss solving trig equations. We have a couple examples here that we'll get through. So the key to solving an equation with a trig function is to isolate your trig function first. So to isolate this, I'm going to subtract 3 from both sides, then divide by 2. So I get 2 sine of theta equals 1. Divide by 2, I get sine of theta is equal to 1/2. And then you're going to have to just use your knowledge of trig to answer. Now there's an infinite amount of answers, but we're going to just focus ourselves between 0 and 2 pi. What do? Sine, when is sine 1/2? I think sine deals with my vertical. This is my thought process. Might not be yours. So I need a vertical distance that's 1/2. So I go to my unit circle in my brain, and I think of a vertical distance of 1/2. Well, that's when we go up less than we go over. So that creates this 1/2 root 3 over 2, 30, 60, 90 triangle. Or that's a situation when we're at a pi over 6. We go up 1/2, down 1/2. Okay, so that's a good start. I know when the vertical is 1/2, I'm at a pi over 6. But now, which pi over 6? Well, sine is positive in the first and the second quadrants. So it's at this pi over 6 here, and the pi over 6 in the second quadrant. Which one is that? Well, 1 pi over 6 less than 6 pi over 6, 5 pi over 6. And that is it between 0 and 2 pi. Next one. Yes, question, Mr. Olin. Okay, cool. This is a 6, by the way. If you have something other than just theta, this is the sine of 3 theta, not just the sine of theta. Okay? You cannot remove the 3. It is trapped by the sine. You would have to get rid of the sine to get rid of that 3. Now, we're not going to do that, though. That's not going to help us. We're not going to take the sine inverse of both sides to remove the sine. But you cannot divide both sides by 3 and then solve. You'll see problems like this all year. Here's the key. Replace whatever you have that is not just theta with a variable. It could be x, it could be y.
Teachers, pardon the interruption. This is just a reminder that for 4th period, that softball, women's softball is to meet in the women's field house. And also 4th period JV tennis will meet in S206.
Okay, so then you just solve this one using your knowledge of trigonometry. When is sine equal to root 3 over 2? That's those taller triangles at the pi over 3s. Sine is positive in the first and the second. So I get pi over 3 and 2 pi over 3. I am not done, however. I still need to figure out what theta is equal to. Well, go ahead and replace x back with 3 theta. Divide everything by 3. Pi over 3 divided by 3 is pi over 9. 2 pi over 3 divided by 3 is 2 pi over 9. And that's your answer. Okay, 2 more questions. We have sine and cosine equal to each other. We cannot move x's around. We cannot help ourselves out. So instead of manipulation, we then just think of what is sine and cosine equal to each other? Well, let's think. I know that if I have a pi over 4 angle, we have a horizontal and a vertical distance that are the same, these root 2 over 2s. So that is when sine and cosine are equal to each other. Well, when are they also equal to each other? Well, let's think in the second quadrant. In the second quadrant, this is a root 2 over 2, but this is a negative root 2 over 2. So they're actually opposites of each other. So it's going to be in the first, where we have all. It won't be in the second, because sine is positive and cosine is negative. Now here in the third, sine and cosine are both negative. We'll have that negative distance here, and then we're going down on the vertical distance, so that's negative. So that location as well, but not here in the fourth quadrant, because this will be negative and this is still positive. So we have two answers here for x. We have pi over 4. And then what is this pi over 4 over here? Well, this is 4 pi over 4. Add 1, 5 pi over 4. Finally, the last problem, the tough problem. You really need to know how to do this to be able to do it. You have 2 cos squared theta plus cos theta is equal to 0. And I told you to isolate the trig function first, and I actually cannot isolate this. You know, we have 2, a cosine squared and a cosine. I cannot combine them because this is not like terms. It's not 3 cos cubed theta. This is like almost 2x squared plus x equals 0. And if I had the situation like this and I wanted to solve, what would you do? Well, you'd actually factor out an x, and you'd create 2 different equations. An x and then times 2x plus 1 is equal to 0. Well, using your multiplication property of 0, you know that if this is 0, this whole thing is 0, and then when this is 0, the whole thing is 0, giving you 2 possible answers. X could equal 0 or negative a half. When x is negative a half, this will be 0. So we will have possibly 2, possibly a lot more than 2 solutions here, but it's solved the same way. You start by factoring out a cosine theta. Just like we did over here with the x. But now we have 2 situations. We need solutions from this first part, and we'll need solutions from our second part. So I need to figure out when cosine of theta is equal to 0. I also need to figure out when 2 cosine of theta plus 1 equals 0. Let's see. Cosine theta is equal to 0. When is cosine 0? That is when we're at the verticals and we're not moving to the left or the right at all. So that's pi over 2 and 3 pi over 2. Now, how do I solve this? Well, I have to do my manipulation first and isolate my variables. And then I have to figure out for which angles is cosine negative a half. Well, cosine is the adjacent. One is the adjacent negative a half. It's right here. This distance is negative a half. That creates this angle and this triangle. That is a taller triangle. So that's got to be at a pi over 3. Now, which pi over 3 is this? Well, 3 pi over 3, this must be 2 pi over 3. And this is 3 pi over 3. This must be 4 pi over 3. Those are the 2 angles that creates this negative horizontal distance. So we have 2 pi over 3 and 4 pi over 3 as well. So we actually have 4 possible answers between 0 and 2 pi. All could work for theta in this original equation. We have pi over 2, 2 pi over 3, we'll list them off from the smallest to largest, 4 pi over 3, and 3 pi over 2. All right, thank you.